We have already talked about the real life application of geometry. Now, let's talk about the actual processes of geometry. In this section, we want to practice geometry. Many of the students find this realm of mathematics unforgiving. They have no clue what it is for. Even my son complains that he actually never understood geometry. The reason is that even when it comes to the actual practice and skills of geometry, the students are not taught correctly. Teachers teach geometry like television serial. If you miss one part or you don't understand another part, then this whole series doesn't make any sense. Then, because the series is so long with so many episodes, it's impossible to go back and find out what you missed or what you didn't understand. Consequently, you have a bad experience. So, in this section, I will try to squeeze several years of geometry into 2 slides. In this way, you will be up to date and almost fully conversant about geometry. First, you need to understand the various definitions in order to practice geometry. You can refer to the corresponding box in the 13 components diagram above. I will not be elaborating on the definitions of the various nomenclatures and terminologies. First, because it would be too long and it would again become a series instead of a quick movie. Second, those terms are quite obvious and you must already be familiar with them if you are reading this far. So in geometry, we have to be familiar with the terms point, line, planes, angles, which are usually measured in degrees or radians. Then the most common use of geometry is to find areas, and so the rules and formulas for areas of various shapes are derived in geometry, and all we need to do is to memorize them. The area of a rectangle is equal to the product of its length and width. Also, we need the perimeter of various shapes. For example, that of a rectangle is 2 times the length plus 2 times the width. We also need to find the volumes of various shapes. In the case of a cube, which has all the sides equal, it is equal to the cube of the length. Then there are formulas to find surface areas. Also, the famous Pythagorean theorem, which talks about how the various 3 sides of the triangle are related to one another and how we can find the value of one by knowing the other two. Geometry can also be used to transform shapes using translation, rotation, reflection, and dilation. You will notice that there are various buttons in your edit bar of your gallery of photographs. Then geometry has got its own classification. There are different types of angles: acute, obtuse, right angle, reflex angles, complementary angles, supplementary angles. Also, there are different types of lines, like some are parallel, some are perpendicular. As we have already discussed, there are also various geometric shapes like triangle, square, circle, cube, parallelogram, and so on. Then in geometry, we have to deal with properties of 2 kinds between 2 shapes. The first one is congruence, where the shape and size of those 2 shapes is the same. The other one is similarity, where the shape is the same but the size is different. Now, this was the basics of geometry. The actual beauty of geometry is in proving, using, and discovering new theorems. I will illustrate using the diagram below. Geometry, like other realms of mathematics, is based on levels of truth, as you can see in the diagram. The first level is called axioms. Basically, they are statements about something. here shapes, lines, angles that are so obvious that they don't need any logical proof. Then, based on them, the second layer of truth is proved either to be true or false. These theorems will then be used as new truths to prove or disprove higher truths, like here level 3 truth. That will be done with the combination of level 1 truths, which are axioms. Then as you go on, there will be still higher truths that will be theorems that will be required to be proven using the lower theorems and the initial axioms themselves. All those theorems both have the pure mathematics appeal as well as the applied math appeal, because they can help us quickly understand geometric shapes that we see physically. Let me illustrate what I just said through the example shown in the diagram. So I start with the first axiom, which says if A and B are distinct points, then there is an exactly one line containing both A and B. Based on this axiom, there are many theorems, but here we are going to talk about theorem 5, which is in truth level 2. As you can see by the arrow indicated, theorem 5 was proved just using axiom 1. As you can see in the diagram, there are mainly 4 methods to prove theorems. The first one is the direct proof, where you start with what you've given and logically step by step show conclusion must be true. The second method is called the proof by contradiction, where you assume the opposite of what you want to prove and then show that this leads to the clear impossibility, and thus you prove the theorem. The third one is proof by contrapositive. Here you prove that if the conclusion isn't true, then the initial condition can be true. Finally, in geometry alone, because the other three methods can be used in other realms of mathematics, but the fourth one only in geometry, is a proof by construction. Here you prove something exists by actually showing how to build or find it. So in the diagram, theorem 5 was proved using the proof of contradiction. Similarly, in the next truth level 3, theorem A, which states if two distinct straight lines intersect, they create exactly 4 angles at their point of intersection. Now, this is proved using theorem 5, which states any two distinct lines intersect in at most 1 point. Now, as you can see by the arrow, in order to prove theorem A, you will also need axiom 11, which states any point in a line divides the line into 2 rays. Again, using the direct proof and the contrapositive method, we can prove theorem A. Finally, we have theorem MX in the fourth level of truth. It states if two distinct straight lines intersect, they form exactly 2 distinct pairs of vertically opposite angles. Now, in order to prove this theorem, you need theorem A, as shown by the arrow. You'll also need theorem 5. Also, you'll need 2 more axioms to prove it is true. Axiom 2 states that every line contains at least 2 points, and axiom 3 states that there exists at least 1 point that is not on a given line. So by combining these 2 axioms and 2 theorems, theorem MX is proved to be true. In this way, it will continue on. As I just mentioned earlier, it can be done for the sake of it or in order to solve real-life geometric problem. In this way, geometry has hundreds, if not thousands, of theorems based on dozens of axioms. Doesn't that sound exciting? I realize now, when I look back in my school days, that it is this particular section that I missed as a student of geometry. If I knew this axiom theorem procedure of geometry, maybe I would have become a pure mathematician because of my love to exercise my logical brain. But without being conscious, I know that the hierarchy of truths of geometry has transcended into my thinking style and investigative nature. So even though I'm not aware, geometry did a lot of good for me. But now I know and you know what real geometry is. Theorems build upon theorems, build upon theorems, build upon finally axioms. All this to understand the physical world and its geometry around us.